Welcome to Algebra 2 with Mrs. Bibb. This week we will be looking at graphs of polynomial functions, doing the binomial theorem, and Pascal's triangle. First we're going to look at Student Journal page 79. We're going to see if these four equations are polynomial functions. As I look at these four equations, I think about the criteria to be a polynomial function. You cannot have a variable under a radical. You cannot have a variable in the denominator, which technically means your variable has to have a positive whole number exponent. Because if you have a variable under a radical, that would be like a square root of x, that would be x to the 1/2. If you have a variable in the denominator, that would be x to the -1. As I look at all four of these problems, only one of them is not a polynomial function, and that would be number 2. It is not a polynomial function because of that variable in the denominator. So all the rest of them are a polynomial function. I'm just going to write yes on all of them. I circled that variable so I would know that's why. So yes to number 1, yes to number 3, and yes to number 4. Write it in standard form, which means you put it in descending order. Number 1 is already in standard form. I'm going to put standard form and put a check mark. Next, I am going to state the degree. The degree is, it's not in standard form. Oops. Let me undo that. I'll tell you how I knew when I started to do this. So f of x equals negative 3x to the 4th, largest exponent first, plus 2x squared, plus 6x plus 1. When I looked at the function, I thought the largest exponent was 2, but then as I looked at it more closely, the largest exponent is 4. So the degree is 4. The type of function it is, with a degree of 4 means you have a quartic function, and the leading coefficient is negative 3. Put LC for leading coefficient. So a degree of 4 is a quartic function. A degree of 3 is a cubic function. A degree of 2 is a quadratic function. A degree of 5 is a quintic function. That's all the ones I know. Quintic, quartic, cubic, quadratic, and linear. Number 3, it is already in standard form, so I'm going to put standard form and put a check mark. I have x to the first and I have no x. The next thing I need to know is its degree, so the degree is 1. And then I need to know the leading coefficient, and that leading coefficient is the square root of 15. The last one, it is not in standard form, so p of x equals negative 2x squared plus 3x minus 2 times the square root of 3. I did not name number 3. Number 3 is a linear function. The degree for number 4 is a quadratic function. Oh, no, it's not. It is a quadratic function, but that's not the degree. The degree is 2, which makes it a quadratic function. And then the leading coefficient is negative 2. Moving on to number 5 and number 6, we're going to evaluate the given function for the given value of x. So that means I'm going to substitute 2 in for x. I'm going to do that in just a moment. And then for number 6, I'm going to substitute -4 in for x. So I'm going to do that, and then I'll come back and show you the answer. Okay, so the answers are hopefully -18 and 0. If you get something different, please let me know. I'll be happy to look at it and check it out. I could possibly have made a mistake. Moving on to the next thing. Okay, it says to describe the end behavior of the graph of the function, and you actually do not have to have the physical graph to be able to describe the end behavior. As I look at the leading coefficient of each of these, and I don't necessarily have to have them in descending order to name the leading coefficient. The leading coefficient for number 7 is -3, and the leading coefficient for number 8 is 3. The degree for number 7 is 6, and the degree for number 8 is 5. Since the degree is even, the ends are going to point in the same direction. I'm going to make a couple of notes down here. When the degree is even, then the ends are going to point in the same direction. Okay, as I was saying, I know the degree of each of those and the leading coefficient. Those will help me determine what the ends of my graph look like. When the degree is even, the ends will point in the same direction. And when the degree is odd, the ends will point in opposite directions. So I know when I look at number 7, both of my ends are pointing in the same direction. And we'll talk about which direction here in just a moment. And when I look at number 8, I know that my ends are pointing in opposite directions. Okay, so let's talk about same direction. Either both ends are pointing up or both ends are pointing down for the same direction. And for opposite directions, one end points up and one end points down, and it could either be the right side up and the left side down, or the left side up and the right side down. Our leading coefficient tells us that information. For number 7, since our leading coefficient is negative, then I know both ends point down. And for number 8, our leading coefficient is positive, so I know the right side points up. So this would be what it would look like. Now, to describe end behavior, you always use like this formula, and I'm going to write it below. It looks like this when you're asked for end behavior. As x approaches positive infinity, comma, y approaches, and then you put what direction y is going. And then as x approaches negative infinity, y approaches, and then you put whatever direction it's going. So that's what I'm going to put for both 7 and 8, except I'm going to fill in that blank here. I'll fill in something here and fill in something here. So let's look at the information I have up here. Let me write down what I need first. So the end behavior is as x approaches positive infinity, y will approach something. And then as x approaches negative infinity, y will approach, and then we'll put what it approaches. So the ends of my graph, and let me draw just a little bit better graph. You do not have to, but I'm going to. Oh, let me erase that. We'll fix that. Now I can erase it. Okay, so no matter what the center or vertex of this thing is, the ends are pointing down. So let me show you what this looks like with a highlighter. As x approaches positive infinity, so that's what that green arrow is doing. What's the end of your y doing? Is it approaching positive infinity or negative infinity? that would be negative infinity. And then let me use another highlighter. As x approaches negative infinity, so there's that blue highlighter. As x is approaching negative infinity, what's the end of your graph doing? Well, it's approaching negative infinity also. And that's my end behavior of that graph. Let's do the same thing for number 8. As x approaches positive infinity, y approaches, and then we'll fill that in. And then as x approaches negative infinity, y approaches, and then we'll fill that in. And I'll just use this as my rough sketch. Go back and grab my highlighter. So as x approaches positive infinity, here's the end of my graph. It's also approaching positive infinity. And then as y approaches negative infinity, what's the end of my graph doing? It's approaching negative infinity. And that's what it means by end behavior. Let's look at the next one. It says describe the degree and the leading coefficient of the polynomial function. So to describe the degree, you're going to say it's either even or odd. And for your leading coefficient, it's either going to be positive or negative. And you know that based solely on looking at the graph. And that's just a rough graph. So as I look at that, the ends are pointing in opposite directions. If you look over here, the ends point in opposite directions, then the degree is odd. So I'm going to say degree is odd, and the left side points up and the right side points down. So that graph is rising to the left, which means that the leading coefficient is negative. Okay, moving on to the next graphs. You do not have to graph these. I want you to see the graphs. I'll go insert a link to Desmos so I can graph them for you. You do not actually have to physically draw the graph. I do want you to realize that this graph, the ends will both point down because it's an even degree and a negative leading coefficient. This graph, the ends will point in opposite directions because you have an odd degree, and it'll point, the right side will point up because your leading coefficient is positive. Actually, I changed my mind. If you will, just go type that into Desmos and see what that graph looks like. I hope to talk about what that looks like next week. So if you'll just remind me after you do your notes, because I want to really talk about that description, because it reminds me of something and we can talk about it. And then number 11, if you'll type that one in also, you do not have to physically draw the graphs. Just look at them. If you want to draw them so you'll have them on your paper, that's fine as well. And then we are not doing number 12 at all. When you're going to do these problems, I do not want you to take that binomial and write it the number of times that you have as an exponent. We're going to use Pascal's triangle to expand these products. The first thing you do is add 1 to your exponent. That tells me that I'm going to have that many terms in the answer. So I put 4 blanks. 1, 2, 3, 4. Then what I do is start with this term, and I put it in the blank for every one of these. I know this will seem weird, but I promise it'll work out. So I put x, 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 and I put a times, and now we're going to use the degree. The degree goes on the first x. Then you put descending order. Then you use the second term. You use this 2, and you put that 2 in every spot. So 2 goes in every spot. And you start on the right, since the red highlighted number is on the right, you start on the right and put third power, second power, first power, 0 power. Now we're going to also insert the proper row for Pascal's triangle. I'm going to pause for a minute and talk about Pascal's triangle and how to create it yourself without memorizing that. I want you to see the patterns that are happening. The top row of Pascal's triangle is 1. The second row is still 1s. Now the third row, you have 1s on the outside, and this number is found from adding this one and this one. So that's where the 2 comes from. The next row, 1's on the outside. This number is found by adding this one and this one. So that's 3. And then this number is found from adding this one and this one. So that one's also 3. In the next row, 1's are on the outside. Same kind of pattern, hopefully you catch on. This number is found by adding this one and this one. Then this number is found from adding this one and this one. And then the last number before the 1, this number is found from adding this one and this one. See if you can do the next row. Pause and see if you can get it, and then I'll draw it on there as well. Okay, so there's the last row there that we just discussed. 1, 5, 10, 10, 5, 1. So hopefully you caught on to the pattern. Now how do you know which row to use? When I look at my blanks, there are 1, 2, 3, 4 blanks with letter A. So then that means I'm going to use the 1, 2, 3, the 4th row. So I'm going to insert, let me erase that arrow I just drew. I'm going to insert those numbers as coefficients here. So I'm going to multiply this one by 1. I'm going to multiply this one by 3. I'm going to multiply this one by 3. Multiply this one by 1. Now we're going to do the math. 1 times x cubed is x cubed. 2 to the 0 is 1. 3 times x squared is 3x squared times 2. Plus 3 times x is 3x times 4. Plus 1 times 1, because x to the 0 is 1, times 8. And then get my final answer. X cubed times 1 is x cubed. 3x cubed times 2 is 3x squared times 2 is 6x squared. 3x times 4 is 12x plus 8. That is the answer to letter A. For letter B, we do the same thing, add 1. I think I'm going to change a couple of those exponents. So I'm going to have 4 blanks for letter B. 1, 2, 3, 4. I don't think I'm going to do C. So you can just mark it out. I think I'm going to make this a 4. So we'll do D. And I think we'll do E and F, so we won't do C for sure. Alright, so I'm going to put X in the first spot. going to go in descending order, 3, 2, 1, 0. I'm going to put negative 2 in the second spot. Oops. So negative 2, and start from the right, since this is on the right. We'll start from the right with our exponents in descending order. Third power, second power, first power, 0 power. Then we're going to put in the correct numbers for Pascal's triangle. So I'm going to put times 1, times 3, times 3, times 1. And then I'm going to do the math. 1 times x cubed is x cubed. And x cubed times 1. 3 times x squared is 3x squared times negative 2. 3 times x is 3x times positive 4. 1 times 1, because x to the 0 is 1, times negative 8. So my answer is going to be x cubed minus 6x squared plus 12x minus 8. And although it may not seem faster, I could ratio, and knowing Pascal's triangle, I could finish faster with Pascal's triangle this is also the binomial theorem, and Pascal's triangle, then you could just multiply it out. Now for letter D, I'm going to start over here. It's the far right, or far left, to do letter D. I'm going to add 1 to 4, so that makes 5. I'm going to have 5 blanks. 1, 2, 3, 4, 5. I think I'll do D here and then do E below it. Okay, I'm going to start with X. Remember, I'm going to put X in the first spot of every blank. Start with your largest exponent of 4. 4, 3, 2, 1, 0. Then put times. Put negative 3 in the second spot. Then I'm going to start on the far right and have 4, 3, 2, 1, and 0. And I couldn't see this one, that's why it's not there. Negative 3 to the 0 power. And now I'm going to insert the correct row of Pascal's triangle. There are 5 blanks, so I want the row that has 5 blanks. And that would be this one here. So I'm going to insert times 1 with the first one, times 4, times 6 here, times 4, times 1. And now let's do the math. 1 times x to the 4th is x to the 4th. X to the 4th times 1, 4x cubed, times negative 3, 6x squared, times positive 9, 4x times negative 27, and 1 times positive 81, I think. And then I'm going to multiply. X to the 5th times 1 is x to the 4th. Oops. Minus 12x to the third plus 54x squared minus 108, I think, 108x plus 81. Tell me if I mess up any of my math, just let me know. So that's the answer to letter D. Letter E, we're going to do the same thing. I've got 3 blanks, so I'm going to add 1 and have 4 blanks. 1, 2, 3, 4. In the first spot of every blank, I'm going to put negative 2x. I'll move that over just a little bit. So negative 2x, negative 2x, negative 2x, negative 2x. And this would be 3, 2, 1, 0. And then in the second spot, I'm going to put positive 3. Oh, I didn't put my time signs. I'll go put them. So multiply by 3. Don't really have to have parentheses since it's not negative. Start on the far right. 3, 2, 1, 0. Then insert the proper row of Pascal's triangle. That would be 1, 3, 3, 1, 1, 3, 3, 1. And then 1 times negative 8x cubed is negative 8x cubed times 1. Next, I'm going to have 3 times 4x squared times 3. Then I'm going to have 3 times negative 2x times 9. And then 1 times 1 times 27. So I'm going to have negative 8x cubed for my first term. My second term is going to be 12 times 3, 36x squared. The next term is going to be negative 6 times 9, so negative 54x. And the last one's going to be 27. Okay. Why don't you try letter F, and I'll do letter F, and then I'll show you the answer. Okay, there's the answer to letter F. Apologize for being so quiet on those other examples. I had a student taking an assessment here during my planning time, but there's the answer that I got. Please let me know if you disagree, and let me know if you have questions. The binomial theorem in Pascal's triangle is not too difficult. It's just a shortcut way to multiply, but it's a good way to know. Sometimes you'll be asked questions like, what's the third row of Pascal's triangle? And that's easy to figure out if you actually know what Pascal's triangle is. But I think it's pretty cool that he figured out that as you raise exponents, a binomial to certain powers, that there are relationships between those coefficients. That if you have 6 terms, that you could multiply by 1, 5, 10, 10, 5, 1, and that relationship exists for every binomial that you raise to the 5th power. So anyway, just a really cool, different little thing to talk about. I hope you have a great day, and let me know if you need help.